Everyone. So my name is Arivoli. I'm the co-organizer of Data Writers Meetup Group. First of all, thanks a lot. In this trying times, we have gone to webinar, and this event is coming live streaming from Jerusalem, Israel. And maybe we don't know how long it's going to be. We have to get used to this lifestyle for the meetup for the foreseeing weeks or whatever. So we'll have to get adjusted to this. Okay, and we are recording this, and it's also live on Facebook, so that people can rewatch it later. And I'll give you a brief introduction about ourselves, and then I'll quickly turn it over to our speaker today. So we are a developer-centric meetup group. We are focused on the domains big data, cloud, and data science. Myself and the organizer, we both have our own day jobs. We do this as our hobby, nights and weekends. And so our stats are, we've been doing this for 4+ years. We have about 4,400 plus members, 45 plus events we have hosted, and then we have had 55 plus speakers. We have been fortunate, and thanks a lot for everyone's help here. And we basically do 3 types of events. We do tech talks, hands-on workshops. We have 2 kinds there, half a day and 1 day. Half a day could be like 3 to 4 hours. 1 day is like about 6 to 8 hours. We have done it. And then occasionally we have paired up with others on their hackathons. And all the events here are free. Okay. And I've been fortunate enough to have speakers from Amazon, Google, Uber, Oracle, Databricks, and all the other popular Apache projects like Kafka, Flink, Pulsar, Heron, Bookkeeper, etc. And venues, we have hosted events in many venues in Bay Area, starting from San Jose, McEnergy Center, all the way to east, west, north, south of Bay Area. Okay, and then that's about it. And today we are going to listen and learn from Oren Eini. I mean, he is the CEO and co-founder of. Let me actually flip it over to your screens. Actually, you can take it over. Can you take it over? Yeah. It's about building a grown-up database. We're going to learn about a NoSQL document database, which is actually transactional as well. And so Oren Eini, he's been in the Microsoft technologies and .NET for a long time. And then he has seen time and again the issues or, babysitting of traditional database. And, so he's built this database using AI for indexing and all the other maintenance operations as well. So I will let him introduce about himself and also the RavenDB and the context here. And then so we'll take it over there, okay? Oren, nice having you as a speaker. And this is our first effort where we are actually broadcasting from another part of the world. And I know it's 3:30 a.m. for you. And thanks a lot. Okay, over to you.
Thank you. It's so late here that by the time I'm done, it's going to be really early. And thank you for showing up for this webinar. I was really hoping to be there in person, but unfortunately, there is this tiny annoying thing that happened that caused everything to become a huge mess. So I love doing virtual conferences, mostly because it means that the community is really easy. I had to go downstairs. And the downside of this is that the level of interaction is very different, which is a shame. Because this is the first time that you're doing this webinar, notice that there is a Q&A. There is also a chat. Talk among yourself. I wouldn't be able to notice that while I'm doing the actual talk. I'm not sure how it is right now in the Bay Area, but right now what happened was that we are under quarantine and we are asked not to go outside the house. I'm currently locked in with a 4-month-old and a 4-year-old, and they're driving me crazy. So a lot of this talk is actually about how to avoid going crazy. Now, this is a talk about databases. So the question is, what do you mean by that? How is going crazy with 4-year-olds being bored out of their mind. I was very looking forward to try to find the appropriate turn of phrase there. How it relates to, in any way and shape, to databases. And for the past 10 plus years, almost 12 years now actually, I've been working on RavenDB, which is a NoSQL document database. It's transactional, distributed, all of the good stuff. I'm not really going to talk about RavenDB per se. I'm going to talk about some of the key features and things that drove the design and implementation of RavenDB. In particular, the idea that I want to deal with grownups. And what do I mean by that? So here's a typical example. RavenDB runs on the cloud, it runs on premise, it runs on the edge. There are two cases that are interesting for us. One of them is the restaurant chain, 36,000 location, 1.5 million instances, and the typical administrator, so to speak, is a teenager, minimum wage, doesn't care what's going on. And here we have RavenDB sitting there in all of the point of sales, in the back end of the restaurant, trying to process everything. Another case is a tax preparation software, 50,000 locations. That's actually deployed on customers' machines. So in the case of the restaurant gets to dictate the hardware and the software that is running on the machine. In the case of tax preparation software, whatever goes, which means that in many cases you have to have a product that is able to work in those kind of environments effectively without having any adult supervision, so to speak. So, and that's actually by design. If you think about this, the typical way we treat databases today is like we are dealing with infants. We're dealing with entities that require constant care and supervision. Now, a very long time ago, I used to be a lovely princess and also a database performance consultant. And one of the things that drove me crazy is seeing the exact same issue over and over and over again. And the number one issue that I ran into was this. This is the Amazon web page, the order page. Now, I want you to look at this and consider what is it going to take in terms of database queries to generate this sort of page. So let's see that. We need to read from orders. Now we need to read this order and these products, this order and these products, this order and these products. And as you can imagine, this is not really an efficient way of doing that. If you look at that, we have 9 queries to the database. We have one for each one of the order lines. For each order, we have to get all the order lines. For each of the order lines to get the products. And that's get expensive really, really fast. This is called the select n+1 issue. It's incredibly common. I used to have a bet with my customers. I would go into the application and tell them, I'm going to find you a select n+1 before lunch. And if not, you don't have to pay me. No one ever managed to collect on that. Again, super incredibly and really, really annoying. Now, this is almost trivial example. Let's consider a real world modeling. How many details do we have in the context of a database? For orders, we have order lines, all of those things that you see on the screen. And I actually stopped because I'm run out of room. There's stuff that I missed. And then you realize that here is your database, which is effectively being attacked by your application while you're doing things. Now, this is not something that you typically see when you're developing. When you're developing, you're working on typically small data sets. You're typically working on an environment where you have just one or very few users. So if there's a lot of database traffic, no one cares. especially because in many cases, the database and your application is running on the same machine. But I kept coming into customers and we have a performance problem, and I would run into this issue in various forms. Now, the nice thing about this is that you can use a join. You can join order and organize and payments and discounts. Oh, wait, we are going to have a Cartesian product from hell. So now try to imagine this. The rendering of the order page, which isn't really, this isn't rocket science. This is a bread and butter of business applications. The rendering of the order page has become so complex that they would literally get an outside help to do that because it was horribly broken. Now, I got really sick and tired of that because I kept seeing the same thing. I was really crazy. So what I wanted to build a grown-up database. I want to build something that you wouldn't have to babysit all the time. The reason that RavenDB is a document database is specifically because of this issue. So we'll be able to load an order in one shot. But once I broke through this barrier of let's build my own database, I start dreaming. I start dreaming of a database that doesn't need a babysitter. Database that I could have a grown-up conversation with. Now, what does it mean to have a grown-up database? It's really, really hard to define that, at least for me. But I can tell you that I know when it's not. If you can't take care of yourself, you're not a grown-up. Remember, RavenDB is deployed in thousands of locations with no administration, and it is expected to run. If you need a full-time DBA for each one of those instances, that ain't going to work. So let's talk about how we can avoid the DBA. Now, to be perfectly fair, DBAs can make life so much easier for a database. Because if I can have human-level intelligence driving my decisions, that's amazing. That means that as an author of a database, I can just punt so much stuff. Oh, the humans will decide. I don't need to figure out all sorts of stuff. I don't need to figure out, okay, what should be the throughput rate to the disk? I can make a human decide that. Now, that's actually a really interesting issue. If you look at lower level, if you go below a database, you typically find something called a storage engine. And a storage engine, we're talking here about things like LevelDB, LMDB, RocksDB. You probably heard about those sort of things. RavenDB uses one that we built ourselves called Voron. And RocksDB is a storage engine used excessively in Facebook. It has grown from LevelDB. And one of the things that Facebook did when they built RocksDB was add much more flexibility to the way that you operate the system. To the point where now there are something like 50 configuration parameters that you can tune. And it got to the point where this is so complex that they're not even going to try to tune that. They actually use AI and machine learning to try to find local maximum that would optimize themselves. And I'm looking at that, I'm thinking, it's horribly complicated. And here we have, oh, I will get a human to do that. And at that point, you realize that, wait, humans don't do very well if you give them a matrix of 50 by 50 and tell them, okay, optimize that. Machines don't do well at that rate. So you have to have something better. So one of the design goals that RavenDB had from the get-go, I want to deal without a DBA. I want to be able to just run, and I'm expected to run efficiently and properly in pretty much all scenarios that you have. Let's talk about some of the common issues that you run into. When you run a query in a database, and such as this guy, what are you going to get? You're going to get the results. But the question is how you're going to get them. And here we're going to see something really interesting. If I have a toddler counting on their fingers, they may count like you see on the screen. Now, this is a valid way of doing that. You will get to the right result. It drives me crazy. And it's probably not a good idea to maintain this habit, but it's a valid way of doing that. In the same way, if you look at the query plan that we have here, and you can see something really interesting. We have a full table scan here. It's a cluster index, but this is effectively a table scan. And what's the problem here? We asked the database, find me the users for this email address. And it did. And it did it in a way that doesn't really make sense for many scenarios. What do I mean by that? There is no index for this query. So we have to read the whole table and consider and discard each one of the rows. It gets the job done. It works. It means that you can move on to something else. But the problem here is that there is a huge hidden cost to the whole thing. And the idea here is that if I'm running one-time query, if I'm working on a very small data set, that is an acceptable method of executing this query. But the problem here is that when I'm running this at scale, if I have even hundreds of thousands, it's as low as that, hundreds of thousands of rows in the table, and I have many concurrent queries on that, you're going to see significant load on your database. Now, there is literally no DBA who haven't run into this, who haven't been able to go into a struggling database, define an index, and improve speed by bazillion %. The problem here is that you need this guy. You need someone to guide you and watch over you. And again, it just doesn't work in many cases, especially as things become more and more complex. Let's talk about this guy. We make one small modification to the system and we add an index. And now you can see that instead of a scan, we have a seek, which is great. That's perfectly fine. That's what I want. It means that instead of ON, I have O log of N, and everyone is happy. But notice that now I have to add this guy. And in some cases, we're going to end up with this guy. We're going to end up right back to the scan issue. Now, I'm oversimplifying things. In 99% of the cases, this query and this query are going to have the exact same appropriate query execution plan. But in some cases, it won't. I had several cases where this happened in production. It actually can happen just because, with the same query, because something changed in the internals of the database engines, and the table statistics are out of line, or the query engine made the wrong determination, something like that, and suddenly the cost of doing things skyrocket, and the system goes down. There is a nice discussion of the issue in this Stack Overflow question. It gives some information about, why this may happen. The problem here is that I read it, and again, I build databases for a living. I understand absolutely why in this particular scenario, answering this question, you're ending up with a table scan. The problem here is, again, you need an expert. And this is a trap that you may fall into that can cause severe problems. So let's see what we can do about this. And I'm going to switch over. This is RavenDB. Right now you can see I have a highly loaded system. This is because at this point I'm currently doing a whole bunch of back inserts into the system. Let's stop that. RavenDB, this is the interface that you get. I don't want to get too bogged down with RavenDB itself. The interesting thing that I have to talk about is this, and I want to be able to run here's some results. Now notice something pretty sad. It took us forever to run this query. And the reason that it took us forever is that there were no indexes on employee. Oh wait, there is an index on employee. Or first step. Okay, let's do the other one. Let's do it like this. Here results, and here you can see it took a while, and again. Okay, so now last name is indexed as well. Notice what happened here. I query RavenDB. The query itself gives us information. It tells us, oh, you're going to have queries on this field. Let's make sure that it's indexed. And RavenDB responds by creating the appropriate index for that. We do that on the fly, dynamically, without you really needing to worry about or think about stuff. You made a query, you told me that this is an interesting thing that you want, so we're going to do that. In the same token, I can do this. Let's find everyone who is speaking French. And now my index is going to be also include full text search on the notes field. Now I want to go here. Now, notice something really interesting. You could see before that we had the index by first name, and then first name and last name. And now we have an index on all three of these fields. What RavenDB is doing, it's doing the right thing when you're running. It's going to create appropriate indexes. Indexes that are not interesting are going to be discarded. So over time, the more queries you make, the more information you give RavenDB, the better it is able to design the appropriate set of indexes. Now, there is a whole lot of thinking going on behind the scenes that the query optimizer is using to generate the right indexes and how to do that and how to discard irrelevant indexes and a bunch of stuff like that, none of which that you actually care about. The whole idea is that we know what the queries are. And RavenDB assumes that if you made a query on a particular field, that is an interesting query. There is a very strong likelihood that you want to do it again. Now, notice something really interesting. While I'm doing all of this indexing, I was busy doing writes. Actually, I stopped that, so let's do it again. What you can see here, I have 7.71 million documents, and I'm going to increase that by a factor of 100. So just by 100. And while we're doing that, let's go ahead and run some queries on the orders, which are what we are actually creating a lot of items of. And I think I have this one. And I cheat. I ran this query before. This is why I was able to get this performance. But let's say that what I want yeah, it would help if I close the query. Now what I'm doing, I'm saying go over each one of the line items, find me the product name, do full text search on that. Now, as you can imagine, this is going to take a long time. In fact, it's going to take about 15 seconds. Under these loads, because we are doing also some writes, it might take slightly more than that. Indeed. We introduce an index while we're doing writes. Now, this index is going to run through all of the items, and we have quite a lot of them. But the whole idea and the reason for this demo is that you don't have locks. You don't need to fear the introduction of a new index. For that matter, you can see that the system is absolutely loaded. We're doing quite a lot of writes and indexing. This is a 2-cores machine. And it's running on burstable hardware on AWS. So we are not actually running on something that can typically sustain this kind of load. But the system is working. And that relates to a lot of what I said about being a grown-up database. That means that I don't expect the user to go ahead and decide my resource allocation strategy. It means that if you make queries, we're going to create appropriate indexes and not close the whole system down because, oh, I'm building an index, I need to lock everything. That has a lot of impacts on how you design the system. Because now a lot of the pain points in deployments are gone. Or I'm building a new version of the system. I can run my queries on one system, on the UAT, and take the knowledge about the expected queries and move it to production ahead of time. When I'm pushing the new version, then it's already trained. It's already optimized for the new system. Now, I mentioned this before about RocksDB, but I went and looked into Postgres and MySQL just as an information. And Postgres has just under 300 configuration options. MySQL has upward of 450 options. Now, it's absolutely insane. I don't know how, I don't think that you could actually get a person to know, okay, if I change this, what's going to happen here, and all sorts of stuff, all of the interdependency between those things. RocksDBs with merely 50 configuration options would require you to use AI and a lot of experimentation to figure things out. So this is like having a kid ask you, how should you do this? Should I do this? Should I do that? And as someone who is stuck at home with the 4-year-olds, that gets old very, 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 very fast. So what you want is the other side. You want something that can manage itself. And how do you approach that? In many cases, you approach it by eliminating the option. So let's talk about 2 common cases. One of the more interesting aspects of building a database is the notion of buffer management. How do you store data from the disk without being absolutely hammered by the fact that disks are so slow? And by the way, I'm talking about this being so slow with regards to NVMe and SSD being orders of magnitudes slower than main memory. And I'm not even talking about HDDs and how slow they are. So typically, because of the cost of I/O, databases have to buffer things in memory. And buffer management is a really complex topic. So now you have quite a lot of options that you have to decide. What is my eviction strategy? How much memory should I allocate for buffers? How much memory for query execution, indexing, those sort of things? With RavenDB, we made a conscious decision to just avoid all of that. We can't know that. But you know what's really interesting? There is someone who can, and that's the operating system, because it has a global view of what's going on. The RavenDB doesn't actually use buffers, it uses memory map IO. And we effectively told the operating system, I want you to go and look into how I'm using my memory, how I'm using my IO, and decide for yourself what is the most optimal way based on your own heuristics. Now, this seems like a small thing, but one of the things that we realized after years of running in production, and we had a really major release 2 years ago, was that there are 2 ways that you can manage complexity. One of them is in the case of buffer management, you can write the code to handle that. And that's possible. We have done that. Pretty much all databases has to do that. But the problem here is that if you do that, you accept the full cost of this complexity, which means that now you have to deal with buffer management, eviction strategies, all of those sorts of things. They're complex, they're horrendous. It's very easy to get into really nasty bugs, and it takes a lot of time to fix. At the same time, there is a whole host of other considerations that you have to work with. For example, what if you're not the only process on the machine? It's very tempting to want to say, oh, I can take as much memory as I want. Except that if there are other users on the machine, other users may be the actual web application, business application that uses the database, that's kind of important for the user because they want to put both of them on the same machine. So you have to also figure out how to be a good neighbor. You have to also figure out how to listen to what the system is telling you. And with Windows, there is an easy way to say, oh, the system is under stress. We need to get more memory. With Linux, that does not exist. It's too late for you to do something because you're ready. It's after you hit the emergency brakes, basically. On the other hand, and so what we did, we decided, okay, who has that knowledge and who can manage that better than us? And the operating system can do that. So we designed the system in reverse. First, look at where you're going to run. Look at what the constraints are, and then design the system so it would be able to take advantage of the existing features of the system. Because we use memory map IO, because we design the system so in many cases the prediction of the operating system is going to match what we're going to do, we're able to take on decades, and I don't even know how many man hours that went into optimizing the swap and paging in major operating systems. That's huge. In the same sense, memory management for the overall system. The typical way you would do that if you're running Cassandra or basically any database based on Java, you have to specify what is the heap size. If you go and read Elastic's documentation, they talk about that because that's mandatory. But then you realize that it tends to not really matter. You want to use as much memory as you could because otherwise you're effectively just blocking yourself while there are still memory to be had. And it's get tricky. In many cases, you have to figure out, okay, what is the maximum transaction size that I'm allowed to run, and a whole bunch of other stuff like that. With Raven, we said, you know what? Those options exist. There are all of those options that exist, but I want to be able to make that determination myself. I want to be able to say, you know what? Instead of telling me, oh, a transaction has a max of 8 megabytes or whatever, I'm going to say something different. I'm going to say, okay, let RavenDB itself manage that, and we're going to detect what we have based on the dynamic state of the system. So the actual configuration is a range of values that we are allowed. And RavenDB is continuously able to adjust itself to find the best options within the given parameters. And the whole point is that I want to be able to run production load systems on the default configuration of the database. We consider it an issue in 90% of the cases if you have to modify the configuration. It means that, okay, there is a solution for that particular customer requirement, but that means that we have to figure out why didn't we already handle this scenario? And you can actually see it here. You can see that the system is under load, but we are not seeing overly high query times. We're not seeing the slowness. The reason that you saw the wait here was I'm in Israel and this particular server is in US East, but the query time is effectively instantaneous. Now, what does it mean in terms of what the database engine is doing? Notice that there is no magic algorithm that we invented that could make things go faster. The system here is under load. We are doing quite a lot of work. We are inserting data. We're doing quite a lot of indexing as well, which is why we're seeing the high CPU. But what we're able to say, okay, let us figure out an appropriate way of allocating resources inside the system. So we're not going to see resource constraint that chokes the system. The reason that we're actually only seeing 2,000 writes per second is that we are doing self-throttling. The database knows how much it can accept, and it knows how to handle that. But I didn't have to define anything. That's the default way that things work. Because again, if I'm running this in production, I don't need to have a DBA to come and watch over me. Now, let's talk about distributed. Going distributed is something that is in many cases is both redundant and mandatory, which is funny. It's redundant because if you look at the speed of most computers, a typical machine can run huge amount of load. Just to give you some idea, a Raspberry Pi, we run RavenDB on Raspberry Pi, and I can do in excess of 10,000 queries per second on a Pi, which is on an old Pi actually, and it's ridiculous. At the same time, because I have to also deal with high availability, I have to deal with geo redundancy and all sorts of stuff like that, I have to go with some form of distribution. The problem there is that in many cases, this is where the different nodes start to fight. This is where the level of complexity they have to deal with explodes. And let's talk about exactly why. Configuring replication, configuring distributed state is not a trivial issue. It's a really hard problem. It's a fascinating problem, by the way, and there is a ton of research around that. But it's a really hard problem. You have to configure the servers, figure out how you're going to handle failovers, how you're going to orchestrate everything, update the clients, configure them, distribute state changes, whole bunch of other really exciting stuff that is really, really complex. There is an interesting case study. There was an outage in October 18 on GitHub. They had a network outage that lasted for 43 seconds, which brought down the entire site for over 24 hours. And I would strongly recommend go and read this. There is also my analysis here. And the reason this is so interesting is that it's so predictable. If you look at what happened and where they ended up with, that specific network outage, where some of the nodes see only some of the other nodes, would in 100% result in this scenario that actually happened. But why is it so hard? Why we've been doing that for literally decades. A lot of that, I think, is because the people who are building distributed systems really think about this as let's solve the problem of distributing the data, distributing the computation. But we tend to miss the point of let's treat it as a user experience issue. When we design the distributed nature of RavenDB, we looked into this. Every machine has a check engine light. Every car has a check engine light, because we realized that, if there is no check engine, then people are not going to, basically they're going to run their car until it burns. And if you think about that, that's actually saying something pretty amazing about cars today. I can pretty much not think about the state of my car and trust that the car will tell me where something is wrong. So with RavenDB, we want to get to this level. We want to get to the point where, okay, everything works, and if it doesn't, then we raise a flag to let you know about that. All of the nodes that RavenDB has are homogeneous, so we deploy one thing. There is not 3 different things that you have to deploy just in order to get something working. There is one location in the cluster itself that defines the topology, and failure is expected. And I have it twice on the slide intentionally. Failure is not only expected, failure is routine. That's actually something really, really important. If you look into how people design distributed systems, you hear about Chaos Monkey and introducing artificial failures, stuff like that. With RavenDB, we decided that we have to expect failures all the time. In fact, if I go into this system, and let's look at the state of the cluster. This cluster is about an hour and a half. In that time frame, it ran 20 elections to select the appropriate node to be the leader of the cluster. We're using RAF algorithm for distributed state management. It's not really that important, but given that I'm not facing any actual failure in the cluster, everything is working properly, why did I have 20 elections? And the answer for that is that I put a lot of load in the system. My system is currently running at capacity. So any small hiccup can cause me to miss my deadline and force an election. And this is not a bug. This is actually something that I do by design, because if failure happen all the time, then my code needs to handle that. And if my code handles that all the time, this is code that is exercised, tested, running, working. In distributed systems, there is no way to tell if a machine is down, slow, or stop responding for a while. A GC pause can be a failure. And if the system knows about that and runs with that, things happen so much more easily. In contrast, if you look at other systems, a failure there can be so much more expensive. For example, CouchDB would very quickly try to rebalance the shards of the system. And that's the right thing to do, but it means that, if I just rebooted this machine because I need to apply some patches, I may have something that would impact the entire cluster. And that's something that you're going to want to say hard no to, because now I can't apply patches to my system, because that would cause the system to be down, not because one node is down, but because I'm running at high load and suddenly I have to move quite a lot of data over the network. So we design for failure. We want to design to the point where we just have the check engine light. That, I'm going to pop it out and we're going to see it. Now, another really important consideration is security. And for someone who deals with databases, the top bad story that I can hear is, okay, all of the data is gone. Or worse than that, my data is still here, but someone else has that. So the notion of someone got all my data is really, really scary. Now, security is hard, you have to do some encryption or authentication. There's all sorts of cases that you have to deal with. What algorithm do you use? What is the size of the, how many bits in the key? A bunch of other stuff like that. And you got to do this properly. If you don't use the right nonce for the encryption key, someone can steal it. If you use a weak algorithm or use the wrong parameters for encryptions, then it's hacked. You know what? This is how you do it. There are security best practices. There are the appropriate ways of doing things, and yet I looked at just the past year, and I limit myself to data breaches that happened, that impact 100 million or more users. This is from last month. In this case, this is Microsoft, and this is an Elasticsearch database that was left open with no password. It was supposed to be protected by a firewall rule that would disallow it from being accessed from the internet. Someone changed the firewall configuration, and now it was on the public internet, and 250 million customer records are out there. In December of last year, over 200 million CVs in China. The underlying reason, someone put a MongoDB instance on the public internet with no password. This guy, this is 275 million, I think, from India, same reason. This one, this is Elasticsearch, and again, someone put a database containing customer data in production with no password, access to the public internet. That's, I don't even know how to start. And here's the really interesting things about that. This is not a hacker. This is someone walking on because you put the welcome mat. Now, there are a lot of hacker tools. One of them is called Shodan, and I use the quotes intentionally. They're basically doing scanning of the entire internet, which means scan all 4 billion IPv4 addresses, all of the 65,000 ports on each one of them, and they do that constantly. If you put a new machine on the public internet right now, it's going to be scanned within 1 minute. 60 seconds, you put a machine, someone's going to scan it. That's how bad it is. And you don't need to actually do the scanning. Someone will do it for you, and you can go to Shodan or the other website like that and just get the information. And this is how you get all sorts of interesting deals. Now, I mentioned Mongo and Elastic a couple of times because they are popular and they got a lot of notice when they fail. But the problem is not really Mongo Elastic. They have the appropriate measures to secure themselves. They have that. The problem is that it tends to be really, really complex. If you have a 60 pages security guidance on your system, no one is going to read it. And you have to think in many cases in terms of security, not, oh, what sort of an encryption I'm going to use, not what sort of a model I'm going to use. You have to think if that is a user experience issue. Just like with configuration. Because if this is too complex, people will do the quickest things possible. With RavenDB, this is the setup mode for RavenDB. You have to choose the secure or unsecure mode. Now, you can choose unsecure mode with RavenDB, in which case we will absolutely refuse to run if you give me an IP that's not localhost. There are ways of saying, oh, I want to be on the public internet with no security. You have to effectively say, I know that several times, and you can't mix a secure and unsecure nodes, and the whole thing is designed to make sure that, oh, I want to run on the secure node. And even when you run on the secure node, one of the issues here is how do you ensure proper security? So we use certificates, and we integrate with Let's Encrypt if you just want to click next, next, next. It takes 1 minute to do that. Or you can run your own, but the whole idea is that we treat security as a user experience issue more than anything else. Because if you make it easy, people will actually run a secure system and you won't end up in this list. Databases are complex. And there are a lot of failure modes that are quite hard to figure out. The interesting thing is, okay, I have a failure. What's going on? For example, let's talk about this. Now I'm looking at my system and see that I have a lot of CPU. If I want to understand what's going on, I can look, okay, here's the information. I have lots of writes, I have lots of indexing. That tells me what's going on. The sad part about it, if I just have a failure, and a few of them right here. Here are some issues, connection happening error. I can see this is probably network network stability issue. Or maybe this is because the other side is also busy, so it did not respond in time. Those sort of things. So being able to understand what's going on is important. It's critical to understand where the system is going. So let's see how I can figure out what's going on. The first thing that I can do is just go there and look. And right now I have something that I think is essential for a healthy database and a system. In one click, I can get a zip file that is going to give me everything that, all of the debug information about the current system. And in this case, you can see it actually takes time to generate this because again, the system is under load because we're putting it under load. The other thing that I want you to pay attention to is what it means when the system alerts me. So we have things that are not really interesting. A bad query. I didn't type it properly. But now you can see, oh, I have low this space. I get an alert on that. And that's because I'm burning through the thing very rapidly. I'm going to stop that so I won't actually hit end of this space. But here, this is front and center. If you have a monitoring system, it will pop up there as well. Here are all of the details about what's going on, all of those sort of things. I can look at the CPU statistics and see exactly what's going on. Now, the whole idea here is that I want to be, again, let's talk about the user experience. I have a high CPU issue. I have a problem in production. My first concern as an administrator is just getting up and running. But the second consideration is I want to be able to understand what happened. So the typical mode in many cases would be, okay, grab the debug package and then do whatever it is that I need to fix the problem. The other side here is what happened when I have a lot of, not a concrete failure. This query failed, the database is not responding, those sort of things. I have the most dreaded issue that can come up from a user. It's slow. And the reason it's slow is so hard is that it's very hard to understand why is it slow. Is it slow because we're currently under high CPU, so the query is slow? Is it slow because the disk is loaded? In this case, you can see that RavenDB actually monitor itself And we're going to say, oh, you know what? This is slow. This is actually such a common thing that we created a specific alert for that. Because in many cases, you won't be able to see that. You won't be able to understand that, oh, this is what happened. So the whole idea is that RavenDB has been built specifically in order to allow you to operate it nicely. And that means that configuration mostly happen automatically. We actively gather information about a possibly problematic things, and we allow you to make it very easy to surface those kind of things very easily. And just looking through the logs is not enough. I can look at the logs, and in very short order, I'm going to basically drown in details. You can see that, okay, it's apparently doing some indexing. Okay, doesn't tell me what's going on. I can also take things further, go into a production system, hit OK, and capture some stack traces. You can see exactly what's going on in my system. Apparently, not doing very much. Oh, this is because I'm spending quite a lot of time doing indexing. But the whole idea is that in order to be a grown-up, in order to be considered grown-up, I don't want to be this guy. I don't want to be the person who is saying, you know what, figure it out. You're the DBA, you can go and troll through the system and figure out where things are going. You want to be the person who tells you, you know what, I'm not comfortable with my disk. It's too slow and it's going to impact my performance. And once you get that, and as you noticed here, we also give you specifics about what is the exact path and the time it happened. You can go to your storage team and tell them, oh, what's going on? In this case, by the way, the issue is that I'm running on standard IO, and that's just too slow on the load that I'm putting it, because I burned through all of my IO credits, and now I'm basically running whatever it can tell me. And what you're seeing right here, the moment that it's going to finish loading, is that we're able to go down and look at specific and individual disk writes. And we can look at them globally, and here also the ones for the indexes. And we can look at them globally and see what happened in the disk at any given point in time. So the notion of this timeline view is really helpful for me to see a global view of exactly what's going on with the disk. In this case, maybe I need to move the data and the disk into different spindles. Maybe I can say that, oh, I'm doing too much, those sort of things. But the fact that the information is collected and actionable for you makes a whole lot of difference into the overall operating environment. And we write about 1 hour, so this is time for questions. You can use the Q&A features, and I will answer them as they go along. I hope this has been an interesting topic. I try to cover a lot of the underlying themes that impacted the design of RavenDB and how it and what drove a lot of the design decisions that we did. Sunil is asking, is it compatible with MongoDB? And the answer is that RavenDB is a document database similar to MongoDB. And we haven't actually shown you any of the actual details. So here is a document. Here is a somewhat more complex document. But it's not compatible in terms of the API because when you saw the queries are using a SQL-like syntax. The actual API is much higher level than this. So if we look at some of the demos, Here is a good example of a user session. Everything is totally typed. Listing is transactional across all of that. So it's a very different model, even if the actual design of the documents is very similar. There are also a whole bunch of other things that I won't get into here that give you more flexibility, but that's for another time. Leonid is saying, thank you for the presentation. So thank you for listening. If you have any feedback, I would love to hear it. We have Badamasha. I hope I'm pronouncing this properly. I'm assuming not. Thanks for the great presentation. When query keeps changing, indexes keep changing. So do you expect queries to be consistent for most times? So this is a great question. And the answer here is that there are types of databases. There is OLTP and OLAP, which is probably the most common distinction between them. And if you think about RavenDB sits very squarely, I want to be an OLTP database. OLTP database is being typically used by applications. And applications have a typically very small set of queries that they're making. And once you learn this small set, and I'm talking dozens to a few hundreds, then you're able to optimize yourself very efficiently to answer those queries. And those queries tend to change in one of few ways. If you have some dynamic capabilities for the user, and again, in most cases, even if you have dynamic capabilities, the user is going to settle very quickly on a very small amount of information there, or when you have a new version of the system. When you have a new version of the system, then you're able to learn the new behavior very quickly and adjust to that. So the idea here is that there is loss of flexibility. If you want to run random queries, that's going to be somewhat more expensive. But for the typical business application, OLTP scenarios, you're going to run the same set of queries all the time. And for that, we're going to be much, much faster because of that. Jayar Daha, again, I'm assuming that I absolutely mispronounced the name. Thank you for presenting. Do you have customers in live productions? So the answer for that is that we've been around for over a decade. The actual first production release for RavenDB has been in May of 2010. And we've been building RavenDB for far longer than that. And we have a lot of people in production, 1,000 customers who are deployed in many various fields. Finance, insurance, real estate for some reason. We had a year where I think the majority of our clients came from real estate. I have no idea why. I believe that the complexity and the transaction nature, the complexity of the domain and the transaction nature of RavenDB push us there, but yeah. Do you have any final questions, stuff you would like to know?
Yeah. Hello, this is Arivoli. I had put in a question in the chat for the the discovery of the indexes, indices, and the auto discovering, right?
Yeah.
There's AI behind the scenes?
Yes, to some extent. One of the things that we found is that if you make things more complex, so I don't like the term AI or machine learning for the automatic indexes. And the reason for that is that one of the things that we strive for is predictability. If the system isn't predictable, then as an administrator, as a user of RavenDB, how do I know what's going on? And the way that I think about that is that I want to be able to give a user, here's a set of queries that RavenDB processed. What is it going to do? And I expect a standard user who is not a RavenDB DBA, is not an expert, to be able to give a good guess about what's going to happen. And I think that this predictability is important. For example, and that actually matters a lot. If you can see here that, this indexes has been marked as idle. We haven't queried them in a while, since the beginning of this session. So they're idle, and now RavenDB is not going to spend any CPU cycles on them, except if we have free time. So right now, you can see that the only thing that we're doing is indexing data on a full text search on the orders. So we are 55% capacity. There are idle cycles. So I'm going to process them whenever I have some idle time. So at the same time, if I'm going to have a new index on employees or new index on orders, they are not going to stop this one. We're going to compete with that until they are newer and more up to date than that. The whole idea is that on the one hand, I want to be as predictable as possible. On the other hand, I want to do the right thing. So there is a lot of delicate balances that we have to deal with. But to answer the actual question, yes, there is some AI there, but it's intentionally a highly predictable one. Okay. I think that's it. If you have any further questions, if you would like to know more, go to the website, ping me. I think that my email is in the show notes. And thank you very much.
Yeah, hello, this is Arivali. So thanks a lot, Oren Eini. It's been great learning about RavenDB and also how to behave as a grown-ups in terms of VBA. Okay, so and then also thanks for presenting from around 2:33 a.m. onwards from your part of the world.
Yes.
Okay, so we'll have to get used to this kind of a lifestyle for meetups moving forward, I guess.
Okay. And one last thing, Leonid is asking, do you share the presentation? I will send it to you, and you would send it to the group, I assume.
Sure. Okay. Either you can put it on the comments section on the event page, so everybody can see it, or you can. I have a GitHub repo which I can send details, and you can just do a pull request directly there.
Okay, that's great.
And also your Facebook Live. It's on Facebook Live now. People can also rewatch it later.
Yes, and I will also link it from there.
Okay. Thank you.
Thank you. Goodbye.